Welcome, we're in chapter 3 now, and we're going to learn about the fundamentals of arithmetic. First up, note that children, they have encountered addition even before they've mastered counting. By the first grade, students should be introduced to concrete models for whole numbers and adding of numbers less than 100. We start doing fractions in the 4th grade. 5th grade, we are performing addition with whole numbers and decimals, and then we get to negative numbers by the 6th grade. Let's look at these 4 addition problems. If I was to look at these problems, and you might want to pause this so that you can read them, but numbers 1 and 4, now they're easier for most children because you can make that one-to-one correspondence with your fingers and those problems. Problems 2 and 3 are more abstract because what is 6 ounces and what is 3 feet or 4 feet? That doesn't really make a whole lot of sense. Plus, in numbers 1 and 4, those are what we call discrete numbers. Discrete numbers meaning that they're countable, and 2 and 3 are continuous amounts, meaning that 4 feet give or take, 3 feet give or take, or even 6 ounces give or take. And it won't necessarily be right on the money. That's what continuous means. Where is it exactly right on the money? Here's a visual of these problems, numbers of marbles, numbers of trucks. Those are the 2 discrete models. Notice that 4 feet of ribbon or 3 feet of ribbon, it's an amount that I could cut it here or there and you really couldn't tell any difference there. In using our set notation, you can look at this and see how we have values of each of these different sets and they become parts of a whole. Whereas 3 elements is part of the 8 and 5 elements is part of the 8, and then they become part of an entire unit or that universal set. As children learn about mathematics, they go through many different stages, and these classical stages are listed here. And at the very beginning, a child would take the 2 different groups and then count those 2 different groups to get the total sum. Afterwards, a child, when they count on, they could say, okay, well, this group has 5 in it, so now I can just start at 5 and go 6, 7, 8 to get to the next one, and that's counting on. And here's a visual for those 2 different methods or 2 different stages of a child's learning. The first one, getting those 2 groups together and then adding them, and then afterwards counting on. And in this slide we have this formal definition of taking the 2 sets and joining them with a union or an OR. And the N out front represents number of. So if we say that A is the set of Andy's marbles and B is the set of Bella's marbles, then N of A is how you would pronounce that. That's the number of elements in set A, or the number of Andy's marbles equals A. A very formal way, this is a very mathematical way to write this. If you take set theory, this is how this is represented. And we took you through that in chapter 2. In this slide we're just making sure that we know that the answer is called the sum and the 2 numbers that are being added are called the add-ins. Now, I find this very interesting. We use the number line a lot of times to demonstrate and to explain things to children. However, but research has found that kids don't really understand this model. So it might work for some children, and I definitely would use it, especially in going positive to negative numbers, but it is not something that students or that research has shown that students can grasp a new concept using it until they're taught how to do that. And that is important for you to teach them how to understand that number line. So just as a matter of vocabulary, the distance from 0 to point 1 is called a unit segment, and that distance in between all the whole numbers is the same, just so that we can all be on the same page. We do use a number line to represent time. We do it all the time, and many graphs where you have time versus money, or time versus the speed, or time versus distance, those are represented with number lines, and that's how we build our graphing as well. So it is important that they learn number lines, but using a number line to necessarily gain more understanding on the front end of something might not be the best method to use. And wow, I want you to look at how intimidating this big chart is, and this is what we have students wanting to learn. We want them to learn these properties of addition, and there's 100 addition facts here, and if you just say these are the things you're going to learn, it can be a bit overwhelming. So let's kind of break this down, and if you'll explain why this table works as it does, and how the fact that if you learn 1 plus 2, then you don't need to learn 2 plus 1, because 1 plus 2 is 3, but then you can say that 2 plus 1 is also 3, and using that commutative property. Also, the zero property, or the identity property, is really cool. This whole row here is really easy to learn. This column is also easy to learn, so this identity property works both ways, especially because we have the commutative property that's working with it. So we'll go through those different properties. Identity property means whatever it is you add to it, you get itself back. That's the identity property, and zero is what we call our additive identity. And using this fact would help students make it so that those 20 facts are really easy to learn, the 0 through 9 and back and forth the other way. Formally, this mathematically is called the commutative property of addition, and once they learn 7 plus 5 is 12, then learning 5 plus 7 is very easy, because they know that the commutative property works for addition. Doesn't matter which group I add first. The associative property of addition comes into play whenever we start saying, okay, we'll try to group things that make a 10, try to group things that make a number that is easy for us to add. And that associative property is something that we use, but we don't really call it the associative property when we're teaching it to kids, but it's important that you know what it is. And then the closure property of addition, just that the sum of any two whole numbers is a unique whole number. When looking at carrying and borrowing, it's important to know that they're really the same kind of concept, and it's not two different things that they have to learn. If you can explain it in this way, it's going to make it easier for students when they go to subtraction. We learn how to do everything forwards in mathematics, and then we learn how to do everything backwards. And subtraction is just backwards addition. I love the visuals on this. This is looking at 48 and looking at 26, and how it is that we group these, because we notice that all of these singles will add up to another flat, and that's why we carry. Teaching students just to memorize that we carry is not nearly as important as getting the concept of we're grouping 4, 7, 8, 9, 10. We're grouping these guys right here together and making another flat, and that's why there's not just 6 of them but 7, because these guys right in here make up a flat. So there I have them circled. So those guys make up a flat, so they're going to be another flat, making 7 of them with those 4 left over. And that is what carrying means, and drawing these pictures up there would be a huge benefit to those students that are very visual learners, so that they don't have to memorize, I've got to do this, then I have to do this, and then I have to do this. If it will make sense concretely, and it will make their learning so much more solid, and make it so that they learn other things much better. Here's another method, add up by tens. And this might help some if they liked the number line method, but if you were going to add up, what was it, the 48 plus 26, so you would start at the 48 and then you would add up 10, 20, and then 2 to get to the 10, and then another 4 to get to that 74. So that might be a way a student likes it, and it's vitally important that you are able to explain in many different concrete ways to students how to add, subtract, multiply, and divide. So this is just driving home the fact that we want students to be computationally fluent. We want them to get algorithms that make sense in their mind, and just because it works for one student doesn't mean it'll work for another. So it's best to have all kinds of different methods. And note that we have a system based on place value, but here are Roman numerals, and theirs isn't really on these place values, so they couldn't carry things because theirs is written differently. If I was going to add this, of course I would change it into base 10 and then add it that way and then put it back into Roman numerals. I would have to come up for another strategy if I was going to keep using Roman numerals. So if you're going to teach students how to add 3-digit numbers, you will need to be able to explain the whys of every single step. And you want students to feel comfortable asking why, because if one student has a question about why, you can pretty much be guaranteed that there are several others that do as well. For me, I love these base blocks. They just make total sense to me. That doesn't mean that it works for everyone, but it does work for me. I really like this one. This is 267 plus 133, and I notice that this group of 7 and this group of 3 make up a flat, and that flat means that there are no ones. And then I have 1, 2, 3, 4, 5, 6, 7, 8, 9 flats here. Adding another flat means that one of these long skinnies means that it makes one of these great big squares. So adding these two numbers would make 400 total, or 4 of these big squares, and then none of these skinny ones and none of these ones. But the answer, of course, isn't 4 because we have place values. So here we are adding them up and making these long skinny flats and then totally into the 400. So very beautiful way to show what carrying really means. Here's the common algorithm that you're showed, and you're told to memorize this technique. Put a 0 here, put the 1 up top, add the 6 and 3 and the 1, you'll get another 10, so you'll put another 0 down, and then you'll put another 1 on top, and it is a memorization thing that you have students and it's what would come after the base blocks. If you use a lot of base blocks to begin with, then putting the ones up top isn't something to memorize anymore. It just makes sense. You're like, oh yeah, well, we squished those together and made another one. And here it is in expanded form. Now when we see how numbers are made up or broken apart, it allows us to understand what is really going on. Here's a cool little lattice technique for adding two numbers, and I don't have to carry if I do this. Let's look at what this actually represents. So you'll add the 5 and the 8, and you'll write the 10's place up top and the 1's place down low. Notice the 4 and 2 make 6, so you'll write no 10's, and then you'll put the 6 down low, and 6 and 7 make 13. You'll have 1 10 and a 3 down low. Then whenever you go to add these up, you'll just because they're already in their place value position, you'll just add up the numbers. 3, 6 and 1 are 7, 3 and 0 are 3, 1 and 1 are 1. So let's try one. So here's our problem. So I'm going to make a lattice with some diagonal boxes. Alright, so I put my base 5 facts up here, and the textbook likes for you to do this in different bases because this is unfamiliar to you. This is a little awkward, it's new, and it allows you to kind of get in the shoes of your students who might not have ever seen this before. So I wrote down the base 5 facts, and if you'll recall, that means the 0 through 4 look just like normal, but once you get to 5 you start repeating your numbers, and this would be my ones place and this would be my tens place. So we might say that it would look like this so that I could be consistent here. So 4 plus 1, that would be 5, but that in base 5 is represented as 1, 0. And then 2 and 1 would be 3, so that's a 0, 3. And then 1 and 3 are 4, so that's represented as 0, 4. So if I were to write this down in base 5, this number here is a 0, so I don't have to write that, but then it would be 4, 4, 0, and base 5. So that's how this would be done in a lattice algorithm. And writing your facts out here to the side really helps, so that, because if your answer had been like 7 or something, you go, oh, that's a 1, 2. So I go ahead and write those down if I was going to do this lattice algorithm in a different base. So this is a very common kind of mistake, and these are going to be the kind of mistakes that you will have to you don't just try to get the student to know what the answer is, you try to fix their mistake, because their mistake here is in place value, because this is 3 10s, 8 1s, and 4 1s. So if a student made this kind of mistake, I wouldn't just show them what to do. I would take them back to the base blocks or take them to something that was visual and show that 8 1s and 4 1s, that would make a 12, and show them that this 4 is not in the tens place. Estimating and rounding are very handy skills, and if someone said, if you were to tell someone how much money you had in your checking account, you probably wouldn't go down to the cent, but you might go, oh, I don't know, I got $600 on there, something like that. And that's an estimation or a rounding, and it allows us to be able to give numbers, such as if we want to talk about a dinosaur bone, we don't necessarily know that it is 65.7539 whatever million. We just say, it's about 65 million. Number of hungry children, about 16 million, something of that sort. We use these when we don't really know the exact value, or the exact value changes. Or in measurement, you know, I might be 5'3½", but I mean, is it really a half, or maybe it's a quarter, or so there are limitations to measurement. So some of this is an estimation or rounding. Now, what's very frustrating is there are a couple of different methods to rounding. So you need to know that just because you're rounding doesn't mean you're rounding. There are different techniques, and you can get different answers for that. So here is talking about different things that we might round. Here is one method is this is over. That's not where this was one I was wanting. This is the slide that I was wanting. Anyway, this, if it's 5 is less than 5, you don't really round down, you keep the same. And this rounding down is kind of that makes it sound like you go down below what you are. You don't really round down, you just keep the same. That's what I would say, and I have seen students miss this because they are rounding down instead of keeping the same. But you keep the same, you don't round down. You round up if it's 5 or greater. This is a typical way that we teach it in elementary school. However, what happens is because 1, 2, 3, and 4 stay the same, 5, 6, 7, 8, 9 round up, there's more of those numbers, and so we round up more often than we keep the same. In order to keep it even, this is the method that scientists use, and when students get to physics, chemistry, or physical science, this is the method that's used. And I will tell you, because I've taught physical science and chemistry and physics, students really balk at this. They say, this is not rounding, but this is actually a more accurate way to round. I don't know that I would introduce students to it, but it's important that you might talk about it after they got pretty good at rounding, or if you were in the 5th or 6th grade, you might say, well, here's another method to round, and it's actually more accurate. So in this method, if the digit to the left of the 5 is odd, you round up, and if it's even, you round down. And that's just to make it so that you round up and keep the same. You don't round down. You keep the same and you round up just as many times as you do either one. And this method makes it so it's closer to the actual amount, because it is statistically you're doing it the same amount of times. So anyway, that concludes 3.1, and you guys have a great week, and let me know if you have any questions with the homework.